Participants, it will.
It's recording. Yeah, yeah. I actually paused the sharing. That was what that button was doing. There we go. And we're back. Yeah, the record button was not on. So, yeah. Sorry. No, I blame Zoom. Oh, yeah, actually, folder is right here.
No,
Now that's audio.
presentation.
Yeah. Oh, that's a presentation. It does have the red.
Click on participants, please. That's me.
Ah, there you go.
Yeah.
Good. Thank you. I'll make sure I'm sharing the right screen. I think we created a bottleneck.
I should have tuned it that in order to get travel from the department, show up these events. It's part of the requirement. Not very nice, sorry. Sign up.
Maybe I should have sent reminders to the deans. Round one. No.
We'll figure it out.
Where are all the students? Well, good morning, everyone. It's about 5 after 10. So if anybody needs a little toroid of diabetes, we also have holes too, which are not holes. They're kind of strange. So we still have coffee and donuts if anybody's interested. We'll start in a couple minutes. We did not send out a link to the students. We wanted to encourage the students to come here. So if you have any students that are, have to be away, I think someone said that one of their students is in Ghana. And so we've shared that with them. But if you want to text your friends and have them come here, that would be great. I think we have all of our speakers. Yeah, we have all of our speakers, so we're good to go. Yes, sir. The Zoom link. Dr. Solomon will need the email. He's in Atlanta. Oh, there you go. All right. All right. Since I don't see a large motion towards the donuts, I guess we'll go ahead and get started. Welcome. As most of you know, I'm Professor Ferguson, Director of Physics here at Wichita State. Before we get started, I would like to begin with a huge thank you for our donor with the foundation, Mr. Bill Simon, who is online watching these proceedings, so watch your language. He is a really, really, really nice guy. I've met him several times. I got out to dinner a couple times. And we are really appreciative of his generosity. All right. So yes. You can't see Bill on the screen, but I can. And he's like, oh, stop it. So our outline for today, we're going to hear from 5 of the research groups. And we're going to go in this order. And we have one presentation. So when your presentation comes up, there you are. It'll be your turn. So your name will be in lights, and then we'll start with that. And the speakers are listed here as well. Professor Muther is out of town. He's at a Dune meeting, which is funny because his student, Sushil, is going to talk about Dune. So I guess that works just fine. And then at the end, I do have some awards to give. We're going to do that at the end. And we're hoping everyone's going to use about 10 to 15, 10 minutes or so. Try not to go too crazy. So we're not here forever. We do have lunch downstairs and some posters downstairs. So we'll break from here after the awards, and then we'll go there and see what's happening. Okay. Dr. Ombel.
This one?
I don't have a laser pointer.
I have.
Good.
Okay. Thank you very much. So things I'm going to talk about quantum physics, not quantum physics in a classroom, mostly application of quantum physics. So this is like a web page of my laboratory website. So it's, if you look at the name, it's say quantum science and engineering. So a lot of things we do apply quantum science for device and try to understand some material. And some of the picture right here, it's a magnetic memory device, which we want to study their quantum properties particularly. And let's go to the motivation. Why quantum science and engineering? So if you go up and meet somebody, it's okay, what are you working? Quantum computing, which is everybody think as quantum sciences or engineering together. But it has 4 branches, okay? The first one, most of the time we kind of talk about is called quantum computing, which has its own applications. It's mostly AKA quantum algorithms, okay? You write codes using optical qubit. No problem. And slide back. The second part of that, or second leg, is quantum sensing and metrology. So application of quantum science and engineering in towards sensing magnetic field, sensing Earth magnetic fields, or sensing or measuring something like a distance, and all those kind of stuff, like making a clock, radar, all those applications. Then quantum communication, which is basically, we call it quantum internet, sending information using a regular internet, but encrypted by quantum mechanics, okay? So that's very much all on there. And then all of this, if you want to build anything like a hardware, you need materials, like quantum materials. Now, quantum materials come in various variety. For example, diamond, like a diamond we use for jewelry, is a quantum material, and which basically right here, so like a superconductor. If you want to design some qubit, which IBM already does, some of it, is use superconducting material to develop quantum computer itself. All together is basically it's quantum science and technology. Now, if you look into last, let's say, 100 years, how it's going. So it's not much if you go 1940s around, or even a few decades before, it's kind of growing. But last decade, basically, the growth is tremendous, basically. It's literally exponentially growing, in every field. It's application in biology, statistics, engineering, economics, everywhere. And then if you look, or if you go some of this conference, this is a slide from Chicago Quantum Exchange. They are saying, it's not my statement, that statistics says that today we have 4,000 job opening on this particular domain, and it's about to grow by 800K by 2040 or so, like in next decade. That's the growth projection they're talking about. And of course, the market share is also going to grow accordingly, and which kind of sounds great, but you have to put a little bit of salt on it to look into more details of it. If you look at all the companies came out in the last 10 years, there are some big name, of course, like for example, IBM, Microsoft, they are there, but they have branch which basically specialize on this direction. But most of this company, like this is all US companies. We are talking, there is a dozen, more than dozen in Europe, more than dozen in Asia. Okay, this is all US. If you go to this conference like APS or MRIS conference, you will actually meet them. So these are all mostly startup, and now some of them even publicly traded company, which is last 10 years. It was not there even 10 years ago, 10, 15 years ago. So which is basically the motivation to work on this domain because of just the projection of it. Now, before I move further, let's acknowledge who actually does all the work. So this is my research lab last summer, and this 2% is not from Wichita State. They actually from Kansas Wesleyan University in Salina, part of summer project. So this is faculty and this is student. And of course, our own collaborator here in Department of Chemistry, Dr. Wang, and Charisma is a PhD student, and my other collaborator in Nebraska. We're all working together in one particular project funded by NSF, kind of some right there. And like many of these students kind of here are funded by Bill Simon's summer fellow. Actually, they work in the summer and make this thing happen. So last 1 year, if we look into what we did, all the research we did, it's come out to a few publications, and it's kind of listed right here. One, and you can see this chem physics chem. So chemical physics and chemicals. It's basically pure collaborative project between chemistry and physics, because in the chemistry side, we build material or we grow crystal. In physics side, we measure their properties, okay? So that's recently published, and these 3 more is under review. And some of them are, you can see many institutions actually collaborating, not only Wichita State, Nebraska, some national labs, Ames National Lab, Oregon National Lab. We have to utilize them to get the data. And the recent graduates from the team, from the group is Bikram. He did MS Physics here, now at University of Toledo. Zain, I think he's our BS Physics and Chemistry major, graduating this semester particularly, or a couple of weeks ago. He's going to be in University of Missouri in Columbia, as doing a PhD, or going to do PhD. And Arjun, he's not defended yet. He will defend in the summer. He will be also at the Mississippi State University, going to join biomedical engineering as a PhD. Now, what do we do in terms of research? So out of all this paper we are publishing, so mostly I'm going to talk about this and this too. Okay. And if you are interested, of course, you can go ahead and read them. They are available for archive. Now, the first project is basically quantum engineering. Okay, what engineering means? So chromium telluride is a material. Okay, this material is a magnetic material which typically use, like for example, any magnetic material used for hard drive, memory device. Okay, this is a quantum material, potentially could be useful for those kind of applications. So we want to know, or we basically try to understand how we can tune its property. Property in the sense here, it's listed right here. It's basically anisotropy. It's basically we want to tune its magnetism in general. Now, so you went to the chemistry. Dr. Wang, basically he did some magic and grow a dopant based system on that particular material. So basically taking some chromium atom out and putting some niobium atom to it. Okay. So now if you look into those two atoms, chromium is smaller in size, niobium is bigger in size. And what it actually does. So we went to some theorists at University of Nebraska, but since we do not have much here in Wichita State, they did a DFT calculation, which is kind of shown right here. And what they found, by changing the size of the atom, we can actually change the anisotropy, which is a measure of magnetism, okay, of this particular material. And the reason it is happening because of the spin of this atom, which is chromium, and some of them are niobium. If we replace them, this interaction actually tuned. And that caused this problem, or that's caused this change. Then in my lab, we measure it using a technique called magnetic resonance, which is kind of this, okay? We have a magnet, we have a microwave line, send a microwave, put a detector, and measure microwave power absorption. And this is the real system. This is the detector, this is where the microwave come in. And this is a various concentration of niobium. So it's 0% means no niobium, 20% means 20% niobium doped sample. And if we got very nice signal, and then if we extract this parameter, which is kind of shown right here, actually anisotropy is going down. So whatever theory predict, we can actually conclude that. And various other magnetic properties is changing, is basically making the material a little bit disorder, which is kind of shown by this graph. The second project I'm going to talk about is, again, it's a application of quantum material. So this particular material is commercially available, and it's kind of we are working with it. And suddenly we thought, okay, why not to apply this particular material for a magnetic field sensing? So now, just to give a little brief review, that magnetic field sensing using quantum physics, it's basically a Z-Man effect. Okay, these are the sensor. You can get it in today's system, like a diamond, silicon carbide, NMR, or ESR, any of those. Is use this fundamental equation. Any magnetic field you want to measure, you need to have a frequency. We can create a frequency very well, up to millihertz even, and divide by a fundamental constant, which is gamma, gyromagnetic ratio, nothing else. So if you use this principle even in different planet, it's still valid. So that's the power of quantum sensing. Okay. Now this is the actual device, I think, created by one of the PhD student, and the material is right there. Okay, this is just a microwave transmission line in a fancy way of putting it, and this is the coil to modulate the magnetic field. And this is the material structure. Okay, it's a chromium chloride. It's a two-dimensional material, basically very ultra thin. Now, if you measure it, you are going to see something like this: a microwave absorption as a function of frequency. Like we basically put a microwave source here, scan the frequency, at some point this thing happened. And that center right here, we find out what is that frequency, and if you utilize that equation, gamma is well known, you can get the magnetic field all the way to accuracy of a microtesla. Okay, and if we do it many field range, it work all the way close to zero field. It's not exactly zero, it's like a 40 millitesla to all the way. So far, our magnet only go 1.2 Tesla, but it can go even 10 Tesla. We can easily, and you can see it's a very linear, like a Hall probe, but it's more accurate. It's absolute, means there is no other correction you need to do, because fundamental constant is a constant, and frequency as good as you can measure. Now, if we apply this thing for a dynamic field detection, which is kind of shown right here, so field is jump in a square wave mode, and you can see this this sensor is following that, and this is a sine wave, and you can see it's following the field by itself. And this is recently we, of course, submitted for publication. And also, I think Wichita State is submitting a patent application out of this concept. I think that's it from my side. Any question you may have?
We just do whatever the PowerPoint says.
Yeah, just, that AI generated? Yeah. Can you hear me? Actually, can you hear me out there? Can't hear myself. I can't hear myself. Okay, so, yeah, get your coffee, settle in. Are you taking pictures? Yeah. I didn't fill out the form. That's kidding. There is no form. Was there a form? Okay, so. Oh. Okay, how does this work? It doesn't seem to work at all.
Yeah, the space bar.
Oh, space bar. Okay, so yeah, I'm going to talk about theoretical particle physics at Wichita State University. And I'm going to give you, so here's my outline. I guess it's really the introduction. And I'll try to go really quick because I only have 10 minutes. And in fact, oh my God, somebody put a timer in these slides. Okay. This is going to be, who did that? Did you do that?
Probably would.
Yeah, I think this is like, okay, so why do I think PhD in physics is valuable? Because of money. Just kidding. Now there's lots of jobs out there. So, okay, this is going to get annoying. Many jobs out there. So my research really overlaps with few groups. Computer science. I like to use computers, although I don't build these computers. But I like to use them. So I'm a big end user. So all my students use computing, and they end up getting some software development skills, data analysis skills, which, by the way, finance, if you look at the stock market, it's all numbers, right? So physicists are getting jobs, and and I think that's the value of a PhD. They've been getting jobs for years. It's not a mystery, although some people on this campus find it amazing, but it's not a mystery. The data's there. So, okay, it's called, no, sorry, I do apologize if I'm being a little bit, yeah, sorry. Just cut me off. So, yeah.
Go get rid of those.
Yeah, so we have, so one of my current student is Tunde. He's working on his okay, yeah, so Tunde is working on multi-Higgs production, and so he gave a recent talk at Particle Physics on the Plane. So there's been this conference in Lawrence for every year since 2019, and I've been using this to get my students familiar with communicating to audiences and research. So Tunde gave a nice talk last year. This was an outcome of a independent study, which now he is now a PhD candidate working with me. So, and then I had a couple past PhDs. Tinghua graduated summer 2020 in 23. He's at the University of Delaware. He's an HPC consultant. Of course, that job came out of the fact that he's running all my workloads on various compute systems. Some here at WCU, some of our things like the national or the open science grid. So again, very project-driven approach. You're doing research. Of course, you're driven by your research. You need to solve the problem. You go find the tools, and so along the way, they pick up some very nice skills. And then Bathia, he's an assistant instructor of physics at McPherson College. So, right. So, and in the last since. Yeah, maybe, well, yeah, for the last 6 years, I've made a concerted effort, if I'm writing a paper, to include a student. So these students have had the opportunity to, in fact, they've, last 6 years, a lot of these students have just written the paper mostly and made all the plots. And basically I just sit there and, advise them. So it's I will say these, I don't think I would actually have be standing here as a tenured faculty member if it wasn't for these students and their strong work ethic and their curiosity. They're just, completely willing to learn. And, it's just so many great examples here. And I think, these students reflect our commitment and to education here. So very happy with our students. So, I'm going to say that a number of times. Now, my research is, it goes many ways. If I had more time in the day, I would just do research, but you need to do research and you need to teach. So, and of course, you can fold it in. And so, but a lot of the topics I'm interested in most, like, the Higgs boson, we've discovered that particle in 2012. We also have this question of, people talk about dark matter. We don't know what it is. We've got this neutrino, which has mass. At one point, it was theorized it was massless. So that how do these pieces fit together? And so, I do play around with beyond the standard model quite a bit. That's an interest for me, and that also leads me to developing some simulation tools for the collider experiments. So, and we like to, because our tools live on a computing system, and we've just had a nice growth of our Bioshock system. So I can imagine we get to take advantage of that even more. So, so we do have some interest of getting machine learning, using machine learning to look at these new physics models, and this is actually, especially with the AI tools out there, if you're scared about coding or programming, the AI assistants are very helpful. So I think we're going to see I think we're going to see a lot of research progress. I'm interested in muon colliders. Well, that's a very muon collider is kind of like a long, ways away, maybe, but the muon is it's like an electron, but much heavier. And if we can accelerate them fast enough, and then we can collide them before they decay, we can generate some very interesting, maybe, some interesting physics there. So, so I've been dabbling in that, see where that goes. And then, of course, there's also there's a framework to test the standard model to see what, is there BSM around the corner, and there's a whole framework for that. So we were doing Higgs pair production. I had a student do triple Higgs production. We were looking at the Higgs couplings when they're changed slightly from the standard model. We have a project with our colleagues in Spain who to write a paper on Higgs production plus these extra jets. Now, probably nobody knows what a jet is, but just imagine you have a lot of particle debris and you want to classify it. You just group it together by their energies and how close they are. So that's, usually these detectors are quite messy there. So had some, like I said, our student went to a conference, so that's good participation there. I had Tunde apply for a machine learning for fundamental physics school, and he was accepted there. So I want to just kind of pass it on to any of the students in the audience. There's meetings always, and if you apply, and when you're a student, you'll get money. Now, if you're a faculty member, you won't get money. But so the message, my message is like, if you find these schools or these events, pass them on to your supervisor and let them know. These are good learning opportunities. So take advantage of it out there. Yeah, so this summer we're gonna Tunde is gonna look at double Higgs production. And we have our simulation tool, and we're going to so he's already looked at this framework. So he's going to yeah, we're actually gonna write a paper on this. That's what we're gonna do. And then we are gonna start adjusting these, because one thing we want to do is put in a heavy, sometimes you could have a heavy Higgs decay to 2 light Higgses. That would be a nice feature to have. The experimentalists would really love that. So the goal here is really to make a tool that the experimentalists at the Large Hadron Collider could use straight out of the box. And then, of course, we also get a paper that's peer-reviewed. And then I also have ongoing work with colleagues at University of Kansas. And then, of course, there's another person involved who's at University of Pikeville. Samuel Lane used to work with Ian Lewis. And we're looking at heavy neutral leptons. And of course, heavy neutral leptons, you can search for them at the collider experiment, the LHC, or you can, depending on the mass range you're looking for, you could look for them at somewhat like some neutrino experiments as well. So, okay, any questions? We don't do questions, do we? We can do questions, yeah. We also do clapping. So, yeah.
Mentioned PhD students involved in your work. I know you've dabbled in getting undergraduates involved a little bit. There's a new projects were on how challenging would it be for undergraduates to work with you?
I don't think it's challenging. I think, I did, I actually forgot to highlight this one student. Yeah, I had an undergraduate applied learning student who basically I taught how to use our Monte Carlo tool and build it and stuff, and or yeah, like compile it on Biochock. So yeah, so it's not impossible. It's not impossible, but you need to. I think where it gets hard for some of our undergrads is that they have their classes and stuff. They're supposed to be. That's kind of like the challenge there, and so it's really just time. But yeah, it was a good success there. I wish I would have put it on a slide there, but I overlooked that one there. So any other questions? Oh, I guess we are next. Who's the next person? Astrophysics. You're astrophysics. You do.
You've earned a donut, by the way.
But I stay on time.
It's fine. So, about 30 minutes in, how are we doing? Doing all right? Okay. So, I have 4 students working with me in astrophysics, so I want to talk a little bit about that. Before we do, just very quickly, how do stars, stars are born, they live, they die, and how do we model that? Star life can be anywhere from millions to billions of years. How do we model something like that? One way to do that is to take some observations of this is a globular cluster called Omega Cyn. Omega Centaurus. It is visible in the southern hemisphere in Australia, South Africa, and South America. This globular cluster has well over 500,000 stars within it. And so by looking at the various colors of those stars and graphing them, you see little patterns. And the patterns, so the observations there on the right are the little gray dots. And then the models are being run through those, trying to understand how the stars live their lives. So stars that are various ages will appear in different positions in the color diagram, color diagram. And so stars as they age, if we could watch this happen during our lifetime, which we can't because of billions of years, we would see those stars advance up those lines. And it might look something like this. So this is a model that was done by Alinar. This is a 6 solar mass model, and it goes through all the various phases of birth, life, and now it's going through death. But before it dies, it likes to go through some, the throes of death, I suppose. And it's become what's called an AGB, or a pulsating asymptotic giant branch star. Yeah, that's a mouthful, which is why we say AGB. And if you watch the little pink graph there, you'll notice that the little dot, which is the current position of the star, It is bobbing up and down because it is literally pulsating. It is getting bigger, smaller, bigger, smaller, bigger, smaller, which means it's also getting brighter, fainter, brighter, fainter, brighter, fainter. And as that happens, we can model that. And there's a variety of things that we can learn from these stars. And you might ask yourself, well, that's exciting, but so what? Well, there's many things we can do with AGB stars. All right. And I'm going to say something rather provocative. We got a couple of chemists in here, so why not? Every carbon atom in your body was in one of those stars. Period. Hydrogen and helium, probably from the Big Bang. Carbon, oxygen, probably from one of these stars, very, very likely. Heavy elements, of course, are going to come from neutron-neutron star mergers or supernova, things like that. But all the carbon in your bodies were in these types of stars. So, hey, right there, I'm cool. You know, I'm sold. Let's do it. These stars produce a lot of dust, which is where that material comes from. So stars live. Then, when they die, these stars will become what's called a planetary nebula, and they will puff out their outer atmospheres, and that will then take that dust and enrich material, and then the next generation of stars are born. Okay, so that's how that happens. AGB stars gives us insight into dredge-ups, and the provocative term hot bottom burning, which I've always wondered why we call it that. But at the very end of these stars, a third dredge-up, what that means is during the convective, tumultuous thing that's happening here is we'll have material will reach down to the inner core of the star and then dredge that up to the top of the star, and that's how we make the observations. These stars are galactic tracers, which I'll talk about in just a minute. And then, of course, we've also got wind physics, which is a very interesting aspect of these stars. There are a lot of difficulties. How do you describe mass loss? How do you actually lose the mass? You have to have a wind mechanism, and that has to be done, numerically. How does that happen? What do we mean by a thermal pulse? A thermal pulse is a flash of thermonuclear reactions that occur. So basically, you gain up enough critical mass so that fusion can turn on, and all of a sudden the outer layers go poof, and then it comes back down as it settles. How do we do the efficiencies of the dredge up? That's very, very difficult to discuss. And then what I deal with is the opacity, such as, which opacity model is right, best, accurate. What does that even mean? What do we say when we model somebody? Say, okay, I make this model of this opacity, which is just the interaction of light with material. How does that compare with somebody else's? Is there a right answer? And again, they're just models. So one student, Tanya, has been working on comparing different opacity models and trying to see differences between them. And in this one that I chose from her work last year on the McNair Scholar, you can see large differences there at about 1200, 1500 Kelvin. Why are those differences there? This is something we're still trying to understand with the various codes that we have. The one that she's interested in is the one that says lithium, no lithium, because there's something really funny with that. Because I have to admit this, she brought this to me and she said, "Oh, we got this lithium problem." I said, "No, we don't. Lithium's not important." Okay, maybe it is. I don't know. We're going to try to figure that out. Another aspect of this is we can compute lots of models. So Alinar here, he has done 36 models of various masses and different compositions, graphed them, and is looking at the tip or the top of the red giant branch. And that is a particular location on the HR diagram. And these can now be tracers because they are essentially, if you've seen one, you've seen them all. And if you put them together, their brightnesses versus color difference, you can actually see a trend there. This trend is observed in globular clusters. So using this to kind of identify how these stars are behaving, we can see them now across the universe. Can we use this as a distance indicator? And if we're trying to understand cosmology, distance indicators are very important. Pritam has been looking at AGB pulses. So these are fundamental and overtone pulses that occur at the end of the life of the star. So this is the bigger, smaller that I was talking about earlier. And if you change one aspect of the model, Okay, these are models. We pick a model, boom, here it is. If we change one aspect of the model, the period of those pulses change. Okay, and all we did, or all he did, was change the opacity data. That was it. Okay, he didn't change convection, he didn't change mass, he didn't change Z or the metallicity, he didn't change anything but just the opacity. Use a different opacity calculation, get a very different answer. And so this is something he's going to look into this summer by doing, thank you, Bioshock, over 300 models of various masses, metallicities, and mixing length coefficients. And what I've been interested in, and I'm having everyone kind of work on this, is the idea that as these stars goes through these dredge ups, the abundance ratio of carbon to oxygen increases as material from the center is drug up to the top. These are observable in what are called carbon stars. Okay, if you look at the sun, the ratio of carbon to oxygen in the sun is about 0.2, 0.3, depending on who you talk to. And then after dredge ups, it can be as high as 1, 2, or 3 times the amount of carbon than oxygen. And that completely changes the chemistry. That completely changes what opacity sources are important, because oxygen sources, water, titanium oxide, et cetera, are going to be very different from carbon sources, which is going to be CN, HCN, and CO, CO2. Okay, those are very different types of sources. So these are our summer projects. And if you have any questions, great. And if not, have some more donuts. Thank you. Brian. I think the biggest uncertainty, particularly with molecules, is going to be the quantum chemistry of the molecular line lists, because you need to know the oscillator strengths. And for something like water, you can have upwards of 100 million transitions that are possible within water vapor. CO, CO2, well, CO is not quite as abundant because it's diatomic. It is heteronuclear, but CO can be important. CO2 is rather important, especially in the infrared. And one of the things which we've done in the last few years, Lynn Buckley did a lot of this, and Carrie Arman did several years ago, was to actually update our code with modern data. There's a place out there called ExoMol, and I forget why they call themselves ExoMol, but they do a large number of quantum chemistry calculations, finding those oscillator strengths and those line transitions. And again, water can have millions, hundreds of millions of lines. So that's a lot of the uncertainty. All right. Time to get snappy.
Okay, this is a presentation of the NASA group, which is Professor Meyer and myself, and working mostly with a large number of students that you'll see. And it stems from the idea that you could produce a lot of neutrinos from the sun. You could produce a lot of neutrinos from other solar aspects, such as a supernova. Solar neutrinos are really hard to detect on Earth. Well, they're actually hard to detect anywhere. Of course, as they go up in energy, they become easier to detect. But solar neutrinos themselves are very low energy. And even though they're relatively hard to detect because you have millions upon millions of them going through this room right now from the sun, back in 1970 to about 1994, Ray Davis' experiment using chlorine did manage to observe solar neutrinos captured on chlorine-37, and it produces a conversion electron, but he didn't look for that conversion electron. He just used a molecular sieve to look for the argon-37 being produced. And we were able to see for the very first time that we could detect neutrinos from the sun. Of course, this wasn't the first detection of neutrinos. That's Cohen and Reines at a nuclear reactor. Solar neutrinos are another important aspect of them, is they're a limiting background in dark matter surges. And of course, not only is the sun a source of neutrinos and the most intense source of neutrinos, back in 1987, a supernova occurred in the small Magellanic Clouds, which resulted in 12 events in the IMB experiment here on Earth over a period of less than a second long. But the sun itself does make neutrinos from this fusion process of hydrogen into helium, and you can see it highlighted there, as well as producing a lot of energy. One of the differences between the energy that the sun's producing in the fusion and the neutrinos is that the sun itself is producing these heat in the form of gamma rays being released, as well as energy of the fused particles. But it takes about 100,000 years for that light, for that energy to reach the surface of the sun to make light. And then the light itself, once it's made atomically on the surface of the sun, takes 8 minutes to come to Earth. So really what we're looking at for those experiments that have looked here on Earth at solar neutrinos is that we're looking at the fusion process right now, 8 minutes ago, compared to the light, which is 100,000 years old, and it's the energy boiling to the surface. We stated back in 2016, or this really strange idea back in 2016, that if we take a small 1 kilogram detector and we go close to the sun where Parker Solar Probe was just going, or at the time in 2016, since Parker Solar Probe was going to be launched in 2018, the idea was that, wow, we could get a neutrino flux from the sun that's 1,000 times bigger than we have here on Earth. So a small 1 kilogram detector acts effectively as a 1,000 kilogram detector. Of course, there's other ways to enhance this, like, for example, argon has a very low solar neutrino cross section, whereas gallium-71 is 1,000 times greater. Plus, gallium-71 has a very much lower energy threshold, going down to 0.408 MeV, whereas a lot of these other solar neutrino experiments are actually only looking at the high energy physics with a very energetic 5 MeV and up. So actually this gives you access to about 6 orders of magnitude more neutrinos if you're sensitive all the way down to 0.408 MeV. And it's just the 1 over r squared law. And I said dark matter experiments here on Earth are actually limited by our solar neutrino background. And so if you go away from the sun, out there at the asteroid belt, you're actually talking about solar neutrinos that are 1/10 that of that on Earth. And if you go out to Saturn, 1/100th that of Earth. So, you know, it's interesting. You have a very interesting thing. NASA could do some fantastic things. Jason's an astronomer. Astronomers like the Hubble Space Telescope. Is the Hubble Space Telescope a great telescope? Pretty good. I don't know. It's a very small mirror. It has lots of defects. It really isn't a great telescope. But if you put it above the Earth's atmosphere, it becomes a fantastic observatory. It's a crappy telescope, but it's a great observatory because NASA is able to deliver it to some place where it could do fantastic things with a simple device. Another example of that was the Egret. In 1992, the Egret spacecraft, Energetic Gamma Ray Telescope, was launched above the Earth. It involved a bunch of spark chambers. At the time, I was a graduate student working with a person who eventually got the Nobel Prize. And he said, NASA's doing what? How dumb are they? Launching a spark chamber into space? We haven't used spark chambers in particle physics since 1975. Well, you know, NASA has a great idea here. You could punt kick a spark chamber across the football field, pull it out of the mud. It's still going to work. It's a very robust detector. But NASA put it above the Earth's atmosphere so that high energy gamma rays could be observed. And it's a very simple detector. And it operated for 8 years, and it produced this map of the galaxy in high energy gamma rays. And that's an example of something fantastic that NASA could do, just like the Hubble Space Telescope. You could operate it someplace very special. It doesn't have to be a fantastic instrument, but you could operate it someplace very special and get a great science result. And what I'm saying here is that we could take a neutrino detector and we could get it really close to the sun where we get 1,000, maybe even 10,000 times the solar neutrino flux. We also could reduce the error on the directionality by a factor of 1,000 or 100, 900 actually, but okay, let's call it 1,000. That allows you to do like looking inside the sun's core itself, like with a microscope. But that only solves half the problem. What else is interesting about solar neutrino detectors here on Earth, other than they're super big, and we can make them much smaller, 1,000 or 10,000 the time, is that they're buried deep underground where you can remove all the background radiation. So we had to be clever. We had to come up with a way in which we could actually get solar neutrinos to be identified. And it's this rare 10% mode where a solar neutrino comes in. I think there's a pointer someone said here, right? A solar neutrino comes in, it produces a conversion electron, and 10% of the time it changes the gallium-71, the neutron in it, to a proton, and an excited state of germanium-71 in the M1 nuclear excited state, which lives for a very short amount of time, about 80 nanoseconds half-life. And it emits a gamma ray of a very well-known energy, 175 keV. So that's now a double pulse signal. We've used this technique. Actually, we used this technique for the first time to actually see the neutrino for the very first time in its life with the Conus-Reines experiment, but it was a different technique. They talked about the reactor neutrino producing the conversion positron and a neutron, and the neutron was slowed down until it could be captured. And it was this process here of that's even still used today. The Prospect experiment, Oak Ridge lab next to the HIFER reactor, used hydrogen with antineutrinos, produced the electron, and then you see a secondary neutron captured 180 microseconds later, and it had a threshold of 1.8 MeV, and it produces that secondary gamma of 5 to 8 MeV. And this cleans up the detector so well, you don't need a beta array, you don't need shielding, you operate it right next to a reactor. Our process here, gallium-71, don't forget, it's like the largest neutrino cross-section that exists. It also goes down to an extremely low threshold, so you gain 6 orders of magnitude more neutrinos. And it's an 80 nanosecond half-life, and it produces 175 keV gamma. And there's a whole class of these types of events, gallium, indium for neutrinos, and then for anti-neutrinos, what we did here with Jared and I with tungsten 183. You can see, again, a double pulse, but you can also use silver or thallium. These are all processes we could use to make it now solve the second part of the problem, that we can make a clean signal without huge amounts of shielding by burying it deep underground. That's the goal of this project that we've been working on. And we've had several reviews. We had a NASA funding for a phase 1. NASA funding for a phase 2. We designed a spacecraft with a mission study. We got professionals to review our ideas, and they said that's all great, but you got to do 2 things. You don't know that the double pulse background is on Earth is the same as in space. You really need to measure it because the Monte Carlos aren't designed to look at double pulse correlated interactions. The other thing is, you need to understand how close your electronics could get the secondary pulse to the primary pulse. And so that's a topic of another student, which I'll highlight and allow. But we spent a lot of time. We got the money for a phase 3, build this CubeSat, put it into space. Here's the picture of the actual launch. The actual launch occurred on May 3rd. And although it looked like every other spacecraft Falcon 9 launch that you have seen, in the room next door, we were all gathered together, and it was a bunch of big cheers when our spacecraft launched, even though it wasn't all that unique of a launch. But it was unique for us because it contained our spacecraft. Then about an hour later, we saw our spacecraft being deployed, kicked out of the launch tube, and now we're in orbit. We're in space. We're about to start taking data. We're working on communications issues, which are purely regulatory right now. And then we had a nice smooth ride into space, about 8 Gs max. And we expect to collect data very soon. And the data could be used for lots of things. And let me highlight now what the students are working on. the two main PhD students, Brian Doty, he's working on the same thing Jonathan worked on in the hardware. Jonathan did his mission on the ground and defended in December. And that just told us that we could have one fake event per kilogram of gallium per 3,000 years, which was a nice result, but that's not the result in space, because in space, the lower energy backgrounds dramatically go up, even though we have a little bit of shielding. Brian's going to redo this for actually in space. Brooks is working on how to study that other question that was asked in the phase 2 review. If you have two double pulses, how close can you get them together? Because in a half-life decay, where does the most common event occur? If it decay, it occurs instantaneously after the first signal. And then, of course, then there's a huge long tail. And if you integrate over the tail, how much of a gap can you get between them is the important question to determine how many events we're going to get. This project, though, has generated several side projects. One is that in orbit, we're flying through the solar wind. And Daniel Riker is a NASA Jumpstart student, and he's been studying how to identify solar wind particles using the EDX, or and compare it to E, or delta E over E identification. And he's also now talking about how to use the protons that we identify to then say what the spectrum was in space of those outside the shielding. And so he's hoping to get first data very soon to do a complete analysis of this. And this summer, Jared Horash is working with us on the project as a Watkins Visiting Summer Fellow. And he was one of our undergraduate bachelor's degrees 7 years ago. I think it was 7. Yeah, time flies. He's going to be helping do some of these like rates of solar wind that we're flying through. There's another aspect of the project is that galactic gamma ray bursts, or the response of gamma rays in the spacecraft. It could be galactic gamma rays bursts occur about every 4 times a year, about every 3 to 4 months. And if we could, while we're up there, we might be able to grab a few of them. We have much better energy resolution than the other gamma ray telescopes that are up there. Although they have directionality because they're looking for E plus, E minus pairs, we have much lower. So we can correlate our observation of galactic gamma ray bursts with lots of gamma rays all at one time to when they see one. And we could have much better energy resolution, and we see much lower energy. And so that might be really exciting. Ren is talking about, he's an undergraduate who's working with us. He's going to be looking at how the antimatter that interacts in our detector produces a signal. Why is that interesting? Because there's 2 detectors up in space already that look at this. One is the AMS alpha magnet spectrometer on the ISS, and the other one is the Chinese spacecraft Deep, which was just launched 2 months ago. And they can look at it. They use the antimatter interacting in their detector to infer the dark matter presence. And they've seen, AMS experiment has seen some interesting results. Seth Driggers is going to be helping with is an undergraduate who's going to be helping with gamma ray studies with the galactic gamma ray bursts. SA is working on neutrino and anti-neutrino interactions on matter. Now, we have a lot of students working with us, so I couldn't fit them all on one slide, but other students that are working this summer, Crystal and Guillermo and she's visiting faculty from Bethany College, and she's going to be working with us and Crystal about, could we make a dark matter detector in an asteroid that changes distance from the sun going like the Earth out to Jupiter, and that would have a known solar neutrino background changing, which we could subtract off and see how much other signals are left, which might be attributable to dark matter presence that we're in. Daniel Siddiqui is working on radiation shielding studies in the group, which is a continuation of the shielding that we did, but using a 3D printer with tungsten loaded. They're called fibers? No, tungsten loaded filaments. And Pierce White and Melissa are is a continuation of our undergraduate student, Daniel Wilson, who had spent the last semester with us looking at taking lunar rocks. Well, we don't have lunar rocks, but we have rocks that are similar to lunar rocks. We bombarded them with neutrons and we look at the splashback of neutrons and the splashback of gamma rays and X-rays to look at lunar sample analyzer and lunar rock spectroscopy. Ian Lyon is a simulation of lunar models of radiation distributions. So this is a very, very active summer coming up. It's of course hopefully dominated by the data we're about to take with the spacecraft. But we have a huge group of students, and they're not all fit into that one small room downstairs, mine. They're actually now spread across the 2 rooms and a lab. But we have 2 PhD students, 4 ongoing master's students, 1 Watkins Summer Fellow, 1 visiting faculty member, and 5 undergraduate students all working this summer. So computers are very scarce, but thank God there's Bioshock. And and the lab they'll be using is room 040, and the main office is 007, but some will be overflowing into 011. And so this is a highlight of what our summer goals are and our summer research is. And it's some of them are funded by our grants from NASA. Some of them are being funded by the Bill Simon graduate summer fellowships. And it should be a very active and exciting summer. Questions?
So, the gas 71 had lower threshold energy. Is that because is it an unstable isotope of gallium?
No, it's not. It's very stable. It's one of the lowest, 0.408 MeV. That gains you 6 orders of magnitude more solar neutrinos. It's also 1,000 times better cross-section than water and heavy water, which was used in snow. And it's also 1,000 times better cross-section for solar neutrinos than argon, such as in the Dune experiment. That doesn't mean the Dune experiment and the snow experiment were bad. It just means we have different sensitivity, and which means we could use a much smaller detector. And if you get that closer to the sun, it can even be better. Of course, we're giving up one thing. We're giving up the fact that this double pulse only occurs 10% of the time, which is still okay, because you got orders of magnitude more due to lower threshold, 1,000 times better cross section, and 1,000 to 10,000 times more flux going closer to the sun, where NASA could deliver it. So we could give up a little bit. I would never probably ask you to design an experiment on Earth using gallium-71, since you're better off just trying to see only that conversion electron. So yeah, go deep into ground, buried in a mile or 2 underground, like the Leeds, South Dakota gold mine, or the Snow, which is in Ontario nickel mine. Of course, that's some of the aspect of why we want to put a dark matter detector in the middle of an asteroid, is just have lots of shielding. And although that might sound weird, asteroids are mostly water. And like the ice cube experiment took a big diesel engine, took the surface ice, started melting it, and used it to drill a hole 3 kilometers deep, which they put a chain down of photo tubes every 100 meters, and then 2 kilometers of uninstrumented above it, and then let it freeze. And of course, the stuff at the bottom is under huge amounts of pressure from the top, so it stays crystal clear. It's not that different than what you could do in an asteroid. There was a question over here.
Because you were talking about space issues in the physics department. The library has a lot of space for meetings. Actually, we moved a lot of books to create that space. So, which, by the way, I'm not here at the library now, but very interested in getting people over to the library. Even if you do 1 or 2 meetings, just sit there and occupy the space.
Well, they want to be active. They want to be able to talk to each other.
Well, you could, I think you could talk. Whiteboard.
Yeah. Okay. I'm supposed to hit the next slide. Professor Muther. Oh, presented by Sushma.
All right, how are we doing this? Okay, so Dr. Figge is going to start.
Not here to talk about the technical things. Then when we get to Abdul's slide, since I've worked with Abdul, I'll talk about the work. But Sushil, if I say something wrong, please yeah, please just jump in. Okay, so yeah, so I'm not Professor Muther. He's actually Professor Muther's at the Dune collaboration meeting, which is going on at South Dakota this week. So that's where they're going to build a detector for Dune. So I'm going to talk about what WSU has contributed. And so there's been Professor Muther has been involved in NOVA and Dune, and of course that historically was NOVA, and then Dune is like a new experiment. And so the main thrust of these two experiments is to understand the neutrino. And the neutrino has this interesting behavior where it changes flavor as it progresses from one point to another point throughout space and time. And of course, this is a window into understanding the neutrino masses. So huge progress. I mean, I think I'll be very complimentary. I mean, Professor Muther has put together a very nice neutrino group at WSU. We have involvement, but Holger is involved, Nick is involved, and I just was added in October. And then we have a postdoc, Andrew Dye, who's actually going to be moving here this summer. So you'll be seeing him around. Abdul, Sushil, Nirab, and then Dr. Reed, he just finished his PhD at, is it University of Indiana? Yeah. Yeah. And so he's, okay, I guess I'm done now. Hey, if you know me, it's a standing joke in the department. So, in fact, I had an advisory board canceled over my talking too much. Never mind. I'm just kidding. And then we have an undergrad, Olive Colfett. Olive actually, before I go into all the amazing things people are doing, and by the way, they're doing amazing things. I love, like I say, what is being done here is truly exceptional. Dr. Palash Roy just defended successfully his PhD. So that just happened. And then Olive, she was awarded through Lawrence Livermore National Laboratory, the John Post undergraduate fellowship. So she's going to be spending the summer working at National Lab. And I think this is, again, by the way, Olive is an undergrad. I think this is great stuff here. So plus Olive knows how to use Bioshock and Root and all this other cool stuff. So I mean, the hunger is there. I love it. So the physics goal of NOVA and Dune. So we want to measure these neutrino oscillations. And one of the big things is really, CP violation. We don't know what, we need to understand that. The mass ordering is another question here. So if we can figure out the mass ordering, that would be helpful. So Dune is promising, like, basically getting the mass ordering, the CP violation, and measuring these parameters in a single experiment. So then you can also use Dune to detect neutrinos from space as well. So those would be our supernova bursts. There's going to be sensitivity for BSM physics, including baryon number violation. Of course, baryon number violation is maybe needed. We have this problem. The problem in physics is that we have, well, there's matter, antimatter, and of course, if everything was, we were thinking, well, if since the Big Bang, you would think, well, there'd be the same number of particles and antiparticles. Of course, we wouldn't exist as a result. But so there's this imbalance. And so there really needs to be an understanding of the mechanism. Now, this is where CP violation comes in. There's mechanisms for that. And of course, baryon number violation is one way to do it. There's leptogenesis, there's lepton number violation models out there too. So, so really this experiment is going to really help the theorists, like myself, who, we have all these great ideas, but, at the end of the day, nature is what it is, and we have to, live with its constraints and, conform our models to it. So, okay. So Sushil gets to talk about all the technical things. And I will let him come up here and I put him the mic. Bear with us.
Okay, good afternoon. Not good afternoon. Good morning, everyone. So I'm briefly going to talk about Dune project and the students' involvement in the Dune project. So I'm part of it. By the way, I'm Sushil Sivagudi. And then Nirav is also part of it. And then we have Abdul, and then we have Andrew Rai as well. So he's a postdoc, and he'll be helping us with our research projects during the summer time. So now, let me talk about the Dune deep underground neutrino experiment, which we called Dune. So it is an international project. It is an international project which basically study about neutrino in general. So, but what exactly is neutrino? We are pretty much familiar with what exactly is neutrino. It's a fermion. It's light mass particles, and they are electrically neutral, and that's why it is very, very hard for us to detect them. But still, like scientists are into neutrinos because in the makeup of this universe, because they are so much in abundance, scientists believe that in the makeup of universe, neutrino has a lot of things to say. So, and then so that's the part of the reason why we are studying neutrino. And then so how do we study neutrino then? First of all, we need to produce neutrino beams, right? So neutrino beams, they are produced. So the way it is produced is we'll shoot the highly moving proton on the target, and then we get a neutrino beam. So we get it on the near detector facilities in Fermilab, and then we let them move, travel 1,300 kilometers all the way up to SORF, and then so that's the thing. And then the other thing is at near detector facilities, we basically characterize the neutrino beam. So we characterize the neutrino beam there, and then we study about the properties of neutrino beam there, and then we let them travel long distance, and then let them oscillate, and then again we note down the properties, what kind of changes we see. So that basically talks about the oscillation in general. So for us to explain the oscillation, so we need to be really know about the pure oscillation parameters like CP violation, mass square difference, and then mixing angles, and then mass ordering. So once we know those oscillation parameters properly, then we will be able to precisely measure the neutrino oscillation, right? And then Dune will be doing better at that regard as compared to the NOVA. So, and then onto the temporal muon spectrometer. So you can see the Dune facilities over there, near detector complex there. So you can see the beam moving. So we have NDLAR, we have TMS, and then we have SAND also. So these are three essential components of near detector facilities. And then right now our topic of discussion is the muon spectrometer. It's a temporary muon spectrometer. So did I miss any slide? Oh, no, I didn't, right? Okay. So Oh, so I sent the updated slide. Okay. Oh, okay. Yeah, but yeah, obviously I can say, skip the left side. So obviously, like this TMS, it is a magnetized detector. It is a magnetized detector, and we need them to identify to correctly identify the muon, right? So once we correctly identify the muon, then we will be able to identify the neutrino involved in the interactions, and that will help us to better understand the oscillation. Okay, so this is a magnetized detector. So now actual work, what I'm doing is like I'm working on magnetic field simulation studies that basically translates to like uh, studying about the behavior of muon in the magnetic field. So, but in a real case scenario, the muon would propagate in the TMS in a non-uniform magnetic field. So, so that makes us to like make a mapper. So the idea of making mapper is so that we can see how muon behaves in a non-uniform magnetic field. So, and then basically the idea is to see the bend of the muons or anti-muons in the magnetic field. And then we have a metric called sign distance, which will help us describe the bending direction of the particle track. So for muons, we would say like if sign distance is greater than 0, then it's going upward, then we'll be able to recognize it. And then if for anti-muons, if sign distance is less than 0, it goes downwards. And then it's all about the particle identifications. So on the top, you can see the plot of number of events versus the sign distance. So for a muon, you can see it is peaking at non-zero values, somewhere close to like 50. That means they are bending at a constant field of 1 Tesla. For anti-muons, the events are not so much. So that's why there is bend at non-zero value, but like since the events are low, so we can like really like see like the kind of like uh, curve over there. So if you keep on increasing that constant magnetic field values to 1 to 1.1, 1.2, and so on, then those muon and anti-muons, they would like move away and away. That means we will be able to discriminate the charge properly at higher values of magnetic field. So the idea of creating mapper is like because muon in a real case scenario travels in non-uniform field. So what I'm trying to do is that to identify to improve the charge identifications, and this is the plot with magnetic field mapper. So right now I'm just testing it out. So these are for low events. So I'm going to like produce like uh, uh, large number of events. Obviously, I need to increase POT. So once I do that, then I will be able to say like more clearly, okay, well, fine. By using magnetic field mapper, you can see the distribution peaking at non-zero value. Then we can see like we can easily identify which one is muon and which one is anti-muon, because the whole idea is like this would like separate at like larger and larger values of magnetic field. And I'm also like recently like into like near detector prototype data sets. So Dune has this like a prototype detector. So they have this real data. And then my idea, my current work is to like compare the real data set to like simulated data set. So we already have validation tools for that, and I'm producing the plots. So my work extends this idea by like creating HTML-based comparison pages for easier viewing, and then yeah, the goal is to like compare production version to version, and then the real data to the simulation, and then we can put this online at NERSC, and then it could be like used time and again with proper documentation so that it's become easier for everyone to use it. So you can see near detector prototype model over there, scintillator pins, NDLR modules, which have 4 intervals, and then we have this 2x2 crash tire, and then we can see the UV beam over there, and then this is one of the plots I took out just to like show the comparison between the real detector data set and the simulated data sets. So basically, those are the hits on the detector space. And then, so this is the current efforts from Andrew. I think I won't be able to speak much about this one. So he's our new postdoc. So he'll be working on this during the summer time. Maybe we can have a couple of seconds to look at it. So what he is involved in? So he is involved in some NOVA production, NOVA history analysis, and also dune flex adoptions and spec integration. So he'll be able to tell it better than myself. So, and onto the Neeraj's one. So he's basically in studying, doing studies on TMS standalone, TMS as a standalone detector. So basically what he's trying to do is that he is trying to observe the neutrino interactions in the TMS. So there comes neutrino. Suppose like muon types of neutrino, that's why they are producing muon after interactions with the detector. And then there is W bosons there, the force mediator, and then they are producing hadron also. So muon and hadron. So what Neeraj will be doing is that he will try to reconstruct the muon energy using the 3D track length. And then once he reconstruct the energy, then he will also reconstruct the energy of the hadrons that is inside the TMS. And then he will like add them up, and then he will be able to reconstruct the energy of neutrino. That's what he will be doing. So, and then the preliminary results also, it looks good. You can see the RICO and the true, they are matching because like it's diagonal, right? Little bit up or down, reconstruction would fail badly, right? So reconstruction is working pretty fine. So that means his results are good. And what he could see on the TMS was some muonic activities and non-muonic activities. Non-muonic would be like obviously those hadrons, and then muonic activities means like muons or anti-muons that is produced inside the detector space. So, and then the last one, the formula is written for RICO, and that's the way he will calculate his reconstructed energy by using 3D track length. And then, yeah, I mean, so this is what he has been involved in, and then he will try to defend his thesis on this particular topic in the summer. Yeah.
Change. So that, okay.
Okay, yeah, so we're working on, actually it's kind of a funny acronym there, but yeah, so that there's in Dune, there within the software and computing consortium, there's some interest in, thinking about how do we make our software, our tools portable. And the reason why we want to try to make them portable is we have all these, they call them leadership class facilities. I mean, there's not a lot of them, but the DOE has really put a lot of effort into building up these HPC facilities in our nation. And of course, it's not going to be feasible to just build a supercomputer all over for every campus area. So the encouragement is to take advantage of these resources, and especially for the Department of Energy projects. And so if basically we have a lot of software that has been built taking advantage of NVIDIA GPUs. What we would like to do is have software tools that can use the AMD GPUs or the Intel GPUs, and also CPUs as well. So the idea is to program in a paradigm. So basically, us programmers are just human beings, and so really we want to use a programming framework that is sort of agnostic as to what hardware is. Okay. Now the typical thing with NVIDIA is you program in CUDA, and of course, CUDA's hard. Now, I think, the great thing is, you can put your codes. It's a little bit easier these days because we have this thing called, so it does make mistakes and you have to check it. So one of the things that I've been co-advising Abdul, Professor Muther on this project of portability, and Abdul has been, doing great work here. I mean, again, we're advisors, you're just advising, I'd actually love to code, but, so Abdul's done a lot of the coding. He's even gone and tried something called PyCoc. So Cocos is a framework that's C++ that will do all the communication to the different architectures, and you can really, but then there's this other project called PyCocos, but it's a Python application interface that connects to Cocos. And so he's been, he took his, one of his machine learning models he built and then started using it with PyCocos. And so he's looked at a few, so he's looked at using our GPUs that are on Bioshock. Now we have some A30 GPUs, and we also have some RTX Pros, and he did some testing of that, so which is a great example of, like, if you make the resources available to everybody on campus, they can use them. So that's the last thing I'll say about that. And so, yeah, the summer plan is to continue working on this portability project, and, really look at it. We also have some H200 GPUs he needs to test. We do need to get our hands on some AMD GPUs. So if anybody has AMD GPUs, like, sit in a box, come to me. we'll get them on Bioshock. Well, if they're sitting in a box. And yeah, so I guess that's you, right? Well, look at this. I'm like moving along here. I think we demonstrated that.
Any questions for Terrence?
Yeah, any questions?
As usual?
Yeah.
I think it's funny, Dr. Muther's not here, but his group took the longest.
That's why.
Yeah, that might be, no. Yeah, we had some miscommunication. I mean, it's okay. All right, we have a few awards that we'd like to hand out, so this is gonna be the fun part of the program, I suppose. Before we do this, though, I do need to send one of the grad students on a very dangerous mission. Do I have a volunteer? Maybe Jonathan, would you be willing to do this for me? Oh, wait, where'd Pritam go? You have to go get Danielle, have her come up here. Okay, will you please? No, just have her, just ask her to come upstairs, please. But we do need Pritam. Is he up? I don't know. So the grad students had something for Danielle. She's not here, so I was going to go get Danielle, but Pritam was going to do the presentation. Was one of the other grad students going to do it, or is it Pritam? Well, we hold off. We'll wait a couple pages. Oh, okay, go ahead. Sorry. Found him. All right. So Pritam, we're going to go get Danielle, okay? All right. So a few little, or I'm going to say minor awards just for fun, because we can. I just want to highlight some of the students and some of the good things the students have done. So one of our students had the best poster at GRASP, and I just want to highlight Brooks Hartsock took first place. Congratulations. I had to do that. Very important. We had a student apply to be a student ambassador with the APS. So this is a student that's going to go around to meetings and do a few other things with that, and hopefully help draw some students, not only to WSU, but also just to physics in general. Alinar received that. And I don't know if it's part of the program, but Alinar is actually traveling today. I don't think it's part of this, because this didn't start in July 1, but he is out someplace. He's got like 3 summer schools he's going to go to this summer, so it's kind of interesting. I don't know if we have any undergraduates here. I was hoping Olive would be here, but she's not. The SGA awarded the Excellence in Collaboration, And the excellence in collaboration went to the SPS. So I want to congratulate them on that. And Pritam, you're up. Stick around. What? Oh, Anna left. Okay, well.
You call me, I know.
Yeah. No. What do you need to show?
Poster?
Can you come back into the room?
Yeah, okay.
Please come in.
What happens when we do things live?
Jason, I didn't send you the list. Can I quickly mention the
Go ahead.
scholarship program? So I'm Richard. I was in charge of the scholarship for the undergraduates, and I just wanted to acknowledge we had 4 winners this year. First one was Melissa Ornelas, who was a Roper Scholar. Olive was the recipient of and our Ralph Schenkenbell and the other one. And then we also have a couple of people that also won. Ethan Jaspers, and he was renewed as a Scripture Scholarship. He was the winner. He was he's a couple other ones. William Day is an engineering major who also is a physics major who got some support. Also, Vander Dayton, who's the education into, he's also going to be working with SI this summer to help this. And so those are winners for our scholarship this year.
Yeah.
For next year.
All right, go ahead.
All right, so I'll be talking briefly about what we as graduate physics student club have been doing last semester. So special thanks to Dr. Humble for giving us this opportunity to host physics weekly physics chat and other events standalone as a committee. So he's been working as a mentor with us. He's been guiding us how to do things. And we have Alnur, me, and Prem as part of the committee doing things. So we have, okay, so we had a bunch of faculty, coming to the physics chat. We had Dr. Solomé talking about his research. We had Dr. Figi talking about how to use BioShock and HPC to do high performance computing and all. And we had Dr. Ferguson as well talking about his career and guiding students how to get success in physics and research. And we had a session about graduate students talking briefly about what they have been doing in their research. And it was a brief session where everyone had about 10 minutes of talking in front of a small group downstairs. So and of course we had games in RSE. We reserved pool and bowling lanes, and it was fun. All right, so this was about what we did last semester. These are a bunch of the pictures from some of those events. And we are planning to continue this all next semester as well. Specifically, we want to make things a little bit more organized. We would be inviting graduate students to talk about their research using like PowerPoint slides and all, so that they have an opportunity to present what they have been working on to improve their communication skills and to talk about their research. And we've been actively looking for things we can organize to have technical training for graduate students. You'll get to know about it when it comes. And a bunch of other stuffs are in line. We'll talk about it next semester. That's all. Special thanks to Dr. Ferguson and Department of Physics for supporting us and funding us to do these events. Also, one other thing, we as the members of club, like on behalf of all the graduate students, would like to give a vote of appreciation to two of our members of the department. I would like to invite Dr. Ferguson to give that appreciation to two of them. So the first one is Anna Solomé. She has been working with like graduate students, guiding them as graduate teaching assistants in lab as lab coordinator. So please welcome Anna Solomé.
He's taking pictures. You need to get in here because this is grad student thing.
Okay, Raymond, you also come.
All
All right. And another one, we have Daniel. She's been supporting us as an admin of the department. And
you get a plaque.
Okay.
We could do that. Yes.
Yeah, hope you don't make me look ugly.
All right, so yeah, that's all. We'll keep doing these events and everything that we have been doing last semester in the future as well. And that's all from my side. Thank you.
Where are we at here? I had to change presentations. All right. No, I'm not sharing the screen. That's all right. We can do this way. All right. So with the very generous support of one of our donors, everybody knows who it is. Hi, Bill. With the very generous support of one of our donors, we do have some awards for some students. And we're going to start with an undergraduate research award, which was nominated by Professor Solomé and myself. This is actually a dual nomination. And this student has done a lot of great work in the last 6 to 8 months, working not only with the Jumpstart program, but also just working in Professor Solomé's lab. And that is Daniel Reichert. Congratulations. And I believe we have a token. Nick, do you need to say anything about the tokens?
Yeah, you have to give them back after. Let's see, picture wall is over here.
Picture wall's over there. Okay. Oh, we're doing the picture wall thing. Oh, boy. Okay. Congratulations. I'm working on it here. Oh, you're on your own. All right, we'll move together here. Congratulations.
Thank you.
All right. Okay. The Graduate Research Award was also nominated by Professor Solomé. I think I'm sensing a pattern here. I'm just kidding. And the Graduate Research Award. Okay, sorry, trying to decide what I did with the other one. There we go. Was awarded by someone who has taken over from, I actually had words written out, but I messed it up. So I don't have, so I'm making up what I'm saying right now because I'm ad-libbing. Okay. So suddenly winning elections. Okay, great. Anyway, hey Brooks, how you doing? So Brooks Hartsock. A lot of good work here. Appreciate your diligence taking over for Jonathan and expanding upon what it is that he's doing. Anyway, okay, how you doing?
And always being willing to help every other student.
Always helping every other student. We also have a teaching award. This is for graduate student teaching. And this was nominated by at least 3 or 4 faculty, particularly Anna. This student has been a TA for now 1 year and has done an excellent job in not only taking the astronomy lab to new levels out into space, but also making sure that those students are taken care of, doing outside events, always willing to work, and I was very impressed with Tanya. So congratulations, Tanya. She's not here today. Tanya's not here today, but we definitely have, Tanya gets blue, by the way. Yeah, we're gonna her a medal.
Medals are like the Stanley Cup, you have to give them back.
Are we gonna keep carving on them and keep making them bigger and bigger? A new ring? No, okay. All right. Faculty teaching. Okay, this one I do remember. One of the students said about faculty teaching that, you know, I love physics demonstrations. It's really cool when you throw a ball around the room, but that tug of war, that was awesome. So Reed Bowles. Apparently yours is black. Congratulations.
Cool, thank you.
At least 4 faculty nominated you, by the way.
Oh, thank you.
Have to stand up straight. And the research award for faculty research, which I don't believe has been announced. I don't think anybody knows this, but 2 people. Is that true?
I did.
You don't know who it is? I did. Oh, I didn't tell you. Okay. Well, yeah, spelled right too. I know you did, Danielle. That's why you're amazing. 3 people. Yeah, 3 people know about it. Oh, yes, that's right. You did spell it. Okay. So what we did for the Faculty Research Award is we emailed a quick survey to all the graduate students, waited a week and said, emailed it again and said, come on, you need to do this. It took at least 2 attempts to do this. And so we went through those survey results, and those faculty members nominated 2 or 3 times, like grad students. And a lot of faculty, I mean, there were a lot of single nominations. There was only 1, 3, or 4. Actually, it might have been 4 nominations. Just for working with everyone in the department, always willing to have people come in to the lab, always willing to work with everyone on campus. And it's Dr. Humble. This means next year you get to decide the award. The previous winner gets to decide the next one. So congratulations.
Decided.
Well, to run it. Yeah.
Well,
not to
thank you
decide.
very much for all.
Yeah, your students did great. Yeah.
We need to get a group picture of everybody.
Group picture.
Outside or? No, right here. We're gonna go outside to get a whole group of everyone later. But right. Okay, show the.
Yeah, Simon class of 26.
Okay.
Thank you. Yeah. All right, I quickly counted noses a few minutes ago, and I think everybody's got 2 lunches downstairs. There were a lot of people that did not show up. Dean Eichhorn was here. Oh, Dean Pugh came. Hi, Dean Eichhorn.
I might come for lunch.
They might come for lunch. I don't know. But there were a few other people that I was expecting listed from a foundation, a couple others, but that's okay. Things get busy this time of year and it happens. So we're glad you came, and I'm glad David came as well. So that ends our formal presentations with this part here. We do have a lunch downstairs. It is in 030, and there are boxed lunches available. And send a student up with it. Yeah, we could do the picture now. Yeah, outside. For those of you joining us online, we appreciate you being here. Varun, glad you're here.
Hello. Yes, thank you so much. Wonderful set of presentations. Looking forward to joining and working with everyone, and really excited.
Yeah, glad you're here. Yeah, this is what you look forward to next year when you're here, because Dr. Kamboj is going to start here in August 2nd or something like that as an assistant professor of physics, and then we'll see what happens after that. Huh? It'll be fun. Looking forward to it. Anyway, we appreciate everyone. Appreciate everyone being here. And again, lunch is downstairs, and have a great summer doing all that research.
Everybody who faculty doing summer physics research and all the students doing going outside with the sunlight. I hope it's not pouring down rain. And we're gonna take a picture like we do every year, a picture of all of us. Then you're free to go downstairs and grab lunch. If you could, and then we want to thank Bill.
Oh, yeah.
For all of his generous support. And Varun, thank you for coming. And
Thank you.
we'll sign you off now because we're going to go outside and then we're going to have lunch. Don't forget, there's posters of the students in the hallway. So while you're eating lunch, you can talk with the other students about what they're doing this summer.
Thanks a lot, Nick.
Thank you.
Hey, Bill. Good seeing you again.
Bye.
Good to see you. See you in July.
Stop.